said that double click the component and change the ground to explicit ground node and change the symbol of the transistor to represent a NPN transistor. NPN transistor, explicit ground node. Double clicking ground, explicit ground node. Okay, done. Then port number 1 should be the base, port number 2 should be the collector, port number 3 should be the emitter. Now I'll double click it again and select the layout. Sorry, no layout, symbol. There's plenty of symbols available for 3-port things. And now I select, there's plenty of these. The BGT, BJT stands for bipolar junction transistor. I click this and then it's okay. Nice. Now this is the input port, this is the common ground, and this is the collector. Now I have a transistor symbol. Nice. So it's just double clicking explicit ground node and everything. Then turn the transistor to a common base configuration. Turn it to a common base configuration. In common base configuration, the small signal ground is at base, the input is at the emitter, and output is at the collector. Thus rotate, flip your component and add port 1 to the input, basically the emitter, port 2 to the output, which is the collector, and ground at the base. Very nice and simple, no problems whatsoever. I click and right click, and then I say flip. Now it's flipped. Then I again right click and I rotate. Now take a look. This is nice. Now I add port number 1 to the emitter. Port number 2 to the collector, and ground to the ground. Now the input is at the emitter, output is at the collector, and ground is at, input at the emitter, output at the collector, and ground at the base. Now it's at common base configuration. Then it said, because we are already in part 5, add a Smith chart and draw the output stability circle. You should definitely see that now it's potentially unstable. Thus, common base configuration is more unstable than common emitter. And therefore, it's better in oscillator design. Sorry about the poor English there, it's not quite good. But whatever, I go here. I'll add a Smith chart to the graphs. New graph, Smith chart. Why doesn't it let me do it?
They're not clearing spaces.
Yeah. Okay. Thanks. Now I'll add the output stability circle. Now it's critical. It should be the output. Add measurement circle. SCIR2 is the, by the way, I've forgotten to change the frequency. Sorry, I'll just do this later. But project options, because I will do this at 3.5 gigahertz. 3.5 gigahertz. Apply. Okay. Then I'll add the measurement that is S output stability circle here. And now the source name is critical. That's my schematic number 1. Okay. And let's see what happens. Let's pray. That's it. The dashed line on the circle tells us which side is the unstable one. You probably see that now, let's see, most of the output stability, most of the output Smith chart is unstable. That's nice. That's very nice for oscillator design. And whenever I select the output reflection coefficient from this side, it should give us a negative resistance at the input. Whenever I select, because now the transistor is like you have 1.
Yeah.
The situation is such. The situation is this. When I select row L from somewhere in the unstable side, then the real part of the input impedance should be negative, and then it should be possible for us to create an oscillator. Nice. Then I'll take a look, because I have to follow my own instructions. You may still increase the instability by adding a small inductor between the base and the ground. So if you want to make it even more unstable, you can add a small inductor between the base and the ground. It says add the inductor and tune its value and try to maximize the size of the unstable area. Basically, I would have no reason to do it here because the unstable area is so large already. I would have basically no reason to add the inductor, but in some cases you might have a significantly smaller unstable area, and in that case definitely completely okay to add an inductor.
How small is
Là
the
YouTube
area
con-
with, is that 50-50?
No, I think it should be most of the area should be unstable. Now I'll go to the elements and I'll add an inductor. And let's see what kind of effect the inductor tuning has. When I tune the inductor, it does this. Here it doesn't do much. But in some cases, if your, let's say, transistor is too stable, then you could add the inductor and it might have a significant effect. Then I'll leave it there, no problem. Then I'll just select this. Now it's 0.77 nanohenries. completely okay. And then I'll just check what I asked myself to do next. Finally create another schematic in which you have exactly the same circuit. Why do I ask me to do this? I asked me to create another schematic in which I have exactly the same circuit but replace the port number 2 at the output with the Z-freg component. No, I won't be doing this. I'll probably have to adjust my instructions a bit. I'll basically should probably rename the schematic. Otherwise I will be completely lost. Rename. Transistor is one schematic, and then I'll add another schematic, new schematic, that is called load, or I'll call it just Z-freg. Create. And on this Z-freg schematic, surprise, surprise, I'll add the Z-freg component, which is in the resistor, and I'll add it here. And then I'll add the ground to the other side and one port to the input. Nice, isn't it? And I'll change the frequency to 3.5 gigahertz, and I'll just remove these brackets because otherwise I'm not able to tune it. What did I do?
So this is what we are going to do also.
Yeah, you have to do this as well. And now I'll just play a bit and add the schematics, then I'll show you what's the meaning of this. But the Z-freg component should be tunable like this. The Z-freg component should be tunable. Now I have one schematic with the Z-freg component. That's the load that I want to connect here.
Heikki, if the port in one schematic has the same number as the port in another schematic.
No, it doesn't matter.
They're not connected.
They are not connected, no. A good point, they are not connected. But you have to be careful when you analyze something that you analyze definitely. You have to tell which, if you want to measure S11, for example, of one schematic, you have to remember that you select the correct schematic in the measurements. You probably understand that I could have connected it here directly. I could have connected it here directly. But I don't. For one reason. And now I'll go back to the project, which is here. I'll add one schematic more and I'll call it, for example, the whole stuff. You can do whatever, you can use whatever names you wish. But then take a look in this strange whole stuff. I'll just take from the sub-circuits category, I take the transistor like this, and then I'll take the Z-freg like this. And now I have all this here on one schematic. I have the transistor in one sub-circuit and I have the Z-freg in one sub-circuit. And then I'll add one port to this one. probably understand that now this is the transistor followed by the load, or the Z-FREC component. Now to my Smith chart. What happened? Yeah, it's still there, no problem. I was a bit worried. So now I have the output Smith chart of the transistor here. If I had connected the Z-FREC component directly there, definitely I wouldn't be able to see the output stability circle of the transistor any longer because it wouldn't have a port number 2. Yeah, that's why I want to have this separately. Then I want to see here as well on the same graph, I would like to see my Z-FREC. I'll add a measurement to this Smith chart, which is port parameters S11 of the Z-FREC. I'll analyze it immediately. So now on this Smith chart, I have the output stability circle of this. And then I have the Z-FREC because I analyzed the S11 of Z-FREC there as well. Now basically we definitely can see that the default value was 50 ohms, therefore it's in the center of the chart with before any tuning. But now we can definitely see that the Z-FREC is on the unstable region. Z-FREC is on the unstable region. If I tune it, basically there's no reason to tune it now, but you know, tuning the real part moves it like this. Tuning the imaginary part doesn't do anything because for some reason the max and min value are 1 ohm and minus 1 ohm. But you can see that I'm able to move my Z-FREC wherever. Nice. What I do next is, I think I'll have to explain this more carefully. Sorry. Try to tune the Z-FREC values until the real part of the input impedance is as negative as possible. The real part of the input impedance as negative as possible. You may analyze the input impedance through port parameters, Z parameters Z11. So I take the whole stuff. The whole stuff has the transistor and the Z-FREC. And each input impedance should be negative. Therefore, I would like to see the input impedance as well when I tune my Z-FREC value. And it said that it's easiest to do by having a rectangular graph. I'll add a rectangular graph, new graph, rectangular, called input impedance. I create. And then I add a couple of measurements to that. Add measurement port parameters, but now Z parameter. Z11 is the input impedance. And now for the whole stuff. For the whole stuff. And I don't take the magnitude because the magnitude is always positive. I take the real, okay, I'll take the imaginary value as well. I'll take both the real value and the imaginary value of the Z11 like this. Now I have the real part of the input impedance and the imaginary part of the input impedance. Now only at a single frequency. This is always quite, ökande spänning, as we say in Swedish. Analyze. Take a look. Without any tuning, the imaginary part of the input impedance is, something like 13, 14 ohms. The real part is minus 20 ohms. Now notice, wonderful, how wonderful this all is. The theory basically seems to be correct by taking the Z-frag or the basically reflection coefficient from the output side, from the unstable region, results to a negative real part of the input impedance. That is fine. Now I just tell in the thing that try to adjust the Z-frag value until it's as negative as possible. Now I have to tell you that that's not completely true, because take a look. I start tuning. The maximum value, let's increase the maximum value to 250, for example. Does this have any significance? Yes, it does. I'll increase this to 150 on the, sorry. So, okay, you continue until you reach a proper negative value. And let's take a look where the impedance lies. You could easily, for example, when I did this a couple of days ago again, the whole thing, it was possible for me to get minus 500 ohms. Minus 500 ohms or something, even, with when I tune the inductor value and everything. But for example, you should be happy with 50. You could be already happy with 40. You could be happy with 100. You shouldn't go much above 100. Because the point here is this. The closer it gets to the edge of the stability circle, because here it's negative, here it's positive. But if we take a look on the behavior of the real part, here it might be, here it's negative. When you move here, it's usually more negative. When you approach the edge of the stability circle, it becomes very negative. Negative, 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 really negative, then positive. So it more or less goes, when you approach this area here, it goes negative, 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 until suddenly it becomes positive when you cross the side. So, the closer you are to the edge of the stability circle, usually the more negative the real part of the input impedance gets. Therefore, it's completely okay. But imagine when you realize this, you have to realize it through matching again. You have to realize it through matching. By the way, you don't have to do it in this exercise. I know that it's completely and fully easy for you to do the matching, since you've done it so many times. Now you don't have to do any matching. I save you from this. If you want to do it, it's completely okay. But when you finally would have to do the matching, it's completely easy for you to do it and realize this. But due to the component tolerances, for example, due to the component tolerances and some things, it might, if you're too close to the edge, due to component tolerances, you might slip to the other side. And then it won't be an oscillator. So there should be even more distance. But notice, we are very close to this point, where the impedance is infinite. So for example, here, when you see a slight move, that's already quite a large move in ohms. So for example, when you go from here, for example, the real part is 200 and something. If you go to 300 and something, you only move from here to here. So from 200 to 300 ohms, that should be completely okay. So you should find a point that gives you a sufficiently negative real part. And the last thing that I want you to do, finally, is this. Is it said here? Add either a serial capacitor or a serial inductor to the resonator side to compensate the imaginary part of Z11. What on earth do I mean? I mean this. Now let's assume that I'm satisfied with my tuning. Where is the Z frame? It's here. It's completely a reasonable value, only a couple of hundreds of ohms. Now I'm basically satisfied. And when I take a look on the input impedance, I see this. This is something, and this is something. You should first have a component here that compensates for the imaginary part. Then you add the resonator. This. You can definitely do it by hand, but I'll just add one component and tune its value until this one moves from here to here. Then it's compensated for. Now the imaginary part of the input impedance is positive, isn't it? It's positive. To compensate it, I have to add a negative impedance. Therefore, the component that I connect to the whole stuff, I connect it here to the whole stuff, is a capacitor. Elements, capacitor, capacitor added, connected. I'll do the tuning. Take a look at the input impedance. Here we go. Now again it's very, very interesting.
Oh my god. What happened?
Notice it doesn't affect the real part at all. Nice, isn't it? Now it's done. So our thing looks like this. It's compensated by a cap of something. So in our case, this is a cap. Then I still ask, after this, I ask you to complete a few steps on paper. This is basically done now with the microwave office. We've selected a proper reflection coefficient to the output to create a negative input resistance. We compensate the reactance part of the input impedance with the serial component. Then this resistance, which is the resistance part of the resonator, let's assume that it's done by, let's say, lumped elements, which isn't true in many cases, but let's do it with lumped elements. This value should be the real part of the input impedance multiplied by minus and divided by 3. So for example, if in our case this was minus 30, if it was minus 30, minus times minus 30 is plus 30 divided by 3 equals 10. Then when you calculate the rest, then you only have to select C and L values in a way that this here is fulfilled. This is your center frequency. You select either L or C and calculate the other one. Now I'll close this, which means picture mute. In the exercise, there's one more thing. And the one more thing is